Hello everyone, Um welcome back, and as you are aware we are discussing about the modes in a mesoscopic device, and in our previous class we started our discussion from these two expressions, the expression for the steady state number of electrons in the channel and the steady state current. And in order to sort of understand this term in better detail, we did sort of a thought experiment, or we did a virtual experiment in which we took the ratio of the two quantities, that is the number of electrons at a certain energy E with the current at that energy E. Okay. So, that ratio is essentially turns out to be tau by q, which is also written here, and this happens for large biases when the applied voltages are large. So, for large biases this is what we obtain, and this will in fact pave a way for us to calculate this characteristics time of the device. This will let us calculate this parameter tau e, and from that we can calculate the parameter gamma e, which is essentially h bar by tau e, and from there we can calculate the number of modes, which is given as gamma e times pi times dE by 2. Okay. So, that is the sequence that we will follow. So, so this we have already seen. We as a starting point we take a 2D channel, and the 2D channel is taken just for the sake of better visualization, because we can visualize a 2D material in a much better way. So, the channel has length L, it has a width W, and the density of states in the 2D channel, you might recall, is given as m star divided by pi h bar square. So, in a 2D channel, this parameter dE, which is essentially the number of electronic states per unit energy, will be area times G 2dE divided which will be area times m star divided by pi h bar square. So, in this expression we also, in addition to this term, we also have another term which is written as GV. It is known as the valley degeneracy. So, if there are multiple in the energy band diagram, there are multiple valleys at the same energy level. In that case, multiple electrons can stay at the same energy level, and that give rise to the degeneracy, and that is accounted by GV. But for our current discussion, we can ignore this term GV, and we will discuss about this in more detail later on. Okay. So, as we have seen that for low voltages, F1 is almost equal to F2, and for high voltages F1 is extremely larger than F2. Okay. And in that case, this the ratio between the steady state number of electrons to the current becomes tau by q, and q can be taken here. Now, you might have also seen from experiments that from certain kind of experiments we can calculate the charge density in a material. So, for example, from the Hall experiment we can calculate the Hall effect experiment, we can calculate the number of charge carriers per unit area or per unit volume. So, generally there is this parameter known as the charge density, and in 2D material case this will be known as the sheet charge density, represented as Ns, and this is an experimental parameter that we can calculate in characterization experiments. Okay. And the charge density at a certain energy will be represented as NSE. Now, for large bias limit, we have this ratio between the number of or number of electrons at energy E to the current at that energy E. Okay. So, if we try to see that in terms of, so let us say if we have the charge density in the material NSE. So, in our 2D material, in our 2D channel, let us say this is our 2D channel, and in this channel somehow we are able to deduce the charge density to be NSE, then the number of electrons in steady state at the energy E will be the charge density at that energy times area, and the area of a 2D material is just length times width. Okay. So, this is a straightforward expression. Similarly, the steady state charge in the device can be represented as the charge density times the rate at which electrons are being eliminated from the channel, or the rate at which electrons are getting across the channel, and that is given by the average velocity of electron in x direction. So, average velocity of electrons in x direction times width times q. Okay. So, this will be the steady state current in the device if the steady state charge density of the device is NSE, and this is also, this expression is quite obvious, because NS times NSE tells us about the number of electrons that are getting eliminated, or number of electrons that exist in steady state. Vx tells us about number of electrons or the velocity of electron, and that essentially is the rate at which electrons are getting swept through the device, and if we multiply by width, it will give us the number of electrons getting across the device per unit second, per unit time or per second, and if we multiply that by q, that will tell us, that will essentially give us the steady state current. So, now these the ratio of these two terms n prime e by I prime e is NSE times W times L divided by Q times NSE times W times the average velocity of electrons in x direction. So, NS cancels NS, W by W. So, what we are left with is L by Q times Vx. So, this is what we obtain had we not done any analysis or any quantum mechanical analysis, any mathematical analysis. This is what we obtain from our experimental analysis actually. If we do an experiment on the 2D channel and if we find out the steady state charge density or the sheet charge density in the 2D channel to be Ns, in that case the ratio of n prime e and I prime e can be written as L by Q times Vx, average of Vx, where Vx is the, I would better write it V plus x. V plus x is the velocity, average velocity of electrons in positive x direction. Okay. And from our previous analysis, we found out that the ratio of n prime e and I prime e is essentially tau e divided by q. So, if we equate these two expressions, one expression from our analytical calculations, and second expression from our experimental understanding of the material. In that case, we can write down tau E by Q to be equal to L by Q times average velocity in positive x direction, and the transit time on an average will be, or the transit time of the electron at energy level E will be L by velocity of electrons in the positive x direction. We can leave this parameter E, and now this is the expression that we obtained from the for the transit time or for the characteristic time of the device. Okay. So, from this expression what we see is that if we want to find out this characteristic time, we need to calculate the average velocity of electrons in the positive x direction, and that is what we will try to do in our next, that is our next step, so to say. So, tau E is essentially or I would say tau is L by velocity in x direction, average velocity in. So, in a 2D device, in a device where the channel is 2D and this is in contact with the source terminal and the drain terminal, this is the length of the device, this is the width of the device. Width of the device is W, the length of the device is L. Okay. So, in this case, for a typical electron, for any arbitrary electron, it might, and if this is the positive x direction, the electron can start from the source at an angle theta from the x direction with velocity v e. Okay. So, some electron will start, let us say, with in this direction, some electron will start in this direction. So, this will be the various possibilities that the electron will start from the source to the drain side. Ideally, this theta, the angle at which electrons start from the source, is this can range from minus pi by 2 to plus pi by 2. So, this can be from this angle to right up to this angle in positive x direction. Okay. So, if the velocity of the electron is v e, let us say v e is the velocity of electron in a direction which is at angle theta from the x direction, then the velocity in x direction will be v e cos theta. Okay. But what is this velocity v e here? What is the velocity with which electrons start from the source side? And here the band diagram picture will be slightly helpful for us. So, in the device, if this is the top of the valence band, this is the bottom of the conduction band, and in this case, generally, as you are aware that electrons that are present in the conduction band, only those electrons are involved in the current conduction in the devices. Mostly those electrons are transporting across the device. Okay, so, the electrons present in the conduction band are generally traveling through the channel. Okay. For the electrons in the conduction band, we can write down the energy of electrons in conduction band to be E equals EC plus half m v square. So, the energy that is in excess to the conduction band edge is the generally the kinetic energy of the electrons. So, if electron is sitting here, this much will be the kinetic energy of the electron, and so half mve square will be equal to E minus EC, and this implies that VE is, please keep in mind that m here is m star, because since we are using classical analog of electron, we need to use m star instead of m. So, VE will be equal to square root of 2 times E minus EC divided by m star. This will be the average velocity of the electrons in the, or this will be the velocity of the electron that starts from the source with energy E, and the average velocity of the electron in x direction, positive x direction, will be, if we take the average, that will be essentially so please keep in mind that for positive x direction, the angle theta can be from minus pi by 2 to plus pi by 2. So, the if we take the average over all possible angles, it will be essentially VE cos theta d theta, and this theta may range from minus pi by 2 to plus pi by 2 divided by this average will be given as divided by d theta from minus pi by 2 to plus pi by 2. This will be the average velocity of electrons in positive x direction, because we are taking angles from minus pi by 2 to plus pi by 2. And since VE, the expression for VE does not involve any theta in it, this can be taken out, and the average velocity will be just from minus pi by 2 to plus pi by 2 cos theta d theta. The denominator will be just this will be theta from minus pi by 2 to plus pi by 2, it will just be pi. So, it will be VE by pi times the, if we integrate cos theta with theta, it will be sin theta, and the limits of the integration are from minus pi by 2 to plus pi by 2. So, which will essentially, sin pi by 2 is 1 and sin minus pi by 2 is minus 1. So, that will be essentially 2. So, the average velocity will be finally 2 by pi V E. This will be the average velocity of electrons in x direction. Okay. So, from this, as you might have seen, we can calculate the transit time as well. So, the average velocity in positive x direction is 2 by pi into VE. So, the transit time will be L divided by the average velocity of electrons in the positive x direction. So, if we write it down like this, this will be L divided by average velocity, which is essentially 2 by pi into VE, and VE, if you recall, is 2 by pi, VE is square root of 2 times E minus EC divided by m star. So, this parameter tau will be pi L by 2 into square root of m star divided by 2 times E minus E c. So, that is essentially what it will be for tau E. Okay. Pi times L divided by 2 into m star divided by square root of m star divided by 2 times E minus E c. So, now we are in a situation to calculate this parameter gamma essentially. So, since now we know the transit time in terms of energy values and the device dimension, we can now easily calculate the parameter gamma. So, gamma will be, gamma E is h bar by tau E, and if we put this expression for tau E here, the gamma E will be equal to h bar divided by pi times L into 2 into square root of 2 times E minus E c divided by m star. Okay. So, this is the energy broadening in the channel because of the finite lifetime of the electrons in the channel. And as you might have predicted from this, that now we can calculate the number of modes in the channel using this expression. So, if you recall, number of modes in the channel is gamma E times pi by 2 times d E. Okay. So, if we put this value of gamma E here, it will be, this pi by 2 will cancel by 2 by pi, it will just be h bar by L times square root of 2 E minus E c divided by square root of m star times d E. Now, you might have also sort of understood why we use this factor of pi by 2 in the expression for modes, because finally, this pi by 2 gets cancelled with the 2 by pi which is there in the expression of gamma E. So, this is how we obtain the expression for the number of modes in the channel from our analysis of the transit time in the device. Okay. So, so although we started with a 2D channel, but this kind of treatment is fairly general and it can be generalized to 3D and 1D channels as well, which we will see in the coming class. So, I will let you think more about this expression until next class, and please keep in mind all the approximations that we make while doing calculations. So, with this derivation of number of modes, we conclude this lecture and we will start from this point in the coming class. Thank you for your attention. See you in the next class.